Hello everyone, welcome back to the regular viewers, and for those of you who are not so regular, I seriously recommend pausing the video now and hitting the subscribe button, because if you're watching this video you probably like a few of the other videos that I have planned or have already released in the past. While you are at the subscribe button, try to find the little thanks button if you're feeling extra generous. Okay, jumping on to today's tutorial, we are going to focus on comparing two groups. In this case, we're going to look at non-parametric tests. In the last tutorial, if you haven't watched that, please look at search for video 362 with very similar title, comparing two groups, but there we looked at comparing two groups using parametric tests, and I hope if you watched that video, you know by now when to use parametric tests. Anytime in statistics, when we say parametric, that means at least your data follows certain rules, and typically the most common rule is that the data is normally distributed. We'll learn a few of those in this tutorial as we go along, and as usual, the first few tenths of minutes I should say, is focused on gaining the fundamentals via a few PowerPoint slides. I promise not to make them boring, and then jump into Python code. And as usual, you can find the link to the Python code down below under the description. Okay, enough talking. Let's go ahead and jump. And here is, go ahead and pause if you want. And here is a quick overview of what we are going to cover today. That's a lot. So let's go ahead and jump in. First of all, the dataset that we plan on using is the one we have used in the past, which is UCI Heart Disease Dataset. And it's a medical data set from 303 patients, and it's got 14 columns or attributes, if you want to call that. That includes demographics, the clinical, the lab features, and so on. And the target variable that we are going to, if you're doing machine learning, if you're going to predict, it's going to be presence or absence of heart disease. Basically, for each patient, do they have heart disease or no heart disease, right? So we can actually do a lot of descriptive statistics and these type of tests, because we have two groups. This is ideal data set for us to explore for this exercise. Okay, now the parametric versus non-parametric, again, we covered part of this in the last tutorial. Primarily, the assumption is if you have normalcy and if you have equal variances, then parametric tests are the ones that you need to perform. Even if it's very close to normalcy, even if it's not exactly normal, parametric tests are fine, especially if you have lots of data. But if the rules break there, then non-parametric tests is what you need to perform. Typically, you perform both and then see how they compare. We'll do that as part of this exercise. And also the data type is a normal data, right? So if it's a continuous type of data, we call it interval or ratio, then parametric tests. And in terms of non-parametric, it can work with ordinal data, right? So this is the first, this is the fifth, this is the seventh, whatever. So it can work with that type of data. And parametric tests are usually sensitive to outliers, and non-parametric are more robust to these outliers. And if non-parametric is so excuse me. If non-parametric is so amazing, why not just do that all the time? Because statistical power, parametric tests have much higher power when all these assumptions are met. And usually non-parametric tests have lower power. That's the primary reason. And so the interpretability, the parametric tests, of course, the prerequisite is normality, which means it has to do with something with means, right? So it actually, most of the tests are centered around the means. So it compares the means of these distributions. And in non-parametric tests, you actually compare the distributions and the medians of these distributions. That's a very high level overview. Now let's actually gain knowledge progressively by jumping into it. Now, when do you want to use it? We just talked about when data is not normally distributed and when your variances are unequal between the groups, meaning the distributions are unequal between the groups, and when you have small sample sizes, and of course, if you have substantial outliers, that's when you consider non-parametric tests. There are a few of these non-parametric tests. I'm only going to talk about the top ones that most people end up using, which is I think I'm jumping ahead here a couple more points. That's the problem with animations, right? I thought I'm jumping to the next slide, but again, you can see when you can actually use non-parametric tests. When working with ordinal rank data, we already talked about it. And yeah, nothing more to add there. But I should have animated this slide, but there are a couple that I mentioned that I will cover, which is Mann-Whitney U test is probably the one that you would see all the time when someone reports, because this is very similar to our sample t-test. You perform t-test when the data has normality, right? So if the data is non-normal, meaning obviously non-parametric test, consider Mann-Whitney U test being equivalent to the t-test. How does it work? Well, when you have two independent samples, let's say with heart disease, without heart disease, and in the sample 1 with heart disease, you have N1, like that many measurements. In sample 2, you have N2, that many data points, right? So you have N1 and N2. And then let R1 be the sum of the ranks for observations in sample 1, meaning you rank all of these, and the sum of these ranks is in your sample 1 is R1. Then U statistic is given by this formula. U1 equals to N1, N2, which is size of sample 1, size of sample 2, plus N1 times N1 plus 1 over 2 minus R1. If none of that made sense, hopefully it will in the next couple of slides once you see those. And the U statistic for sample 2, so there are two U statistics you're calculating, one for sample 1, one for sample 2, and the smaller of these two is actually considered to be the U statistics when you're comparing these two. Okay, now let's go one level deep so we can actually look at some test data on the right hand side. I apologize for a lot of text. Hopefully animation should help, but you can pause and go through it at your own pace. So first of all, what do we mean by rank? On the left hand side, I talked about, okay, R1 be the sum of ranks. What the heck is rank? Well, if we want to compare the ages of people in two different groups, for example, group 1 with heart disease, group 2 without heart disease, right? Group A, let's say with heart disease, group B without heart disease. Let's say group A, the age is 45, 65, 54. We have 3 people in group A. I hope you have more people. But for this exercise, let's say you have 3 people. And in group B, no heart disease, you have 4 people. Okay, are these two groups different? Like, does age matter when it comes to heart disease? Well, first let's sort all of these in ascending order, like all these ages. You combine group A and group B. You have, in our case, 4 plus 3, right? 7 total population. So you order them ascending order in this case, and then you assign a rank. Like lowest age or youngest age is 45, oldest age is 65, and 45 is rank 1, rank 2, rank 3, rank 4, rank 5, and so on. And now group A, look at the rank. 45 is rank number 1, 65 is rank number 7, and 54 is rank number 4. You just sum all of those, you get 12. Group B, you sum all of those, you get 16. And that's exactly what R1 on the left-hand side means. You know, the sum of ranks for observations in sample 1. So if you do this, now our N1 equals to 3, N2 equals to 4, our rank for the one, total sum of ranks for 1 is 12, and you plug that into your equation, you get U1 is 6, and U2, in this example, we get same value for U1 and U2, but obviously it will be different, on real data sets. So in this case, for this specific data, the Mann-Whitney U statistics is 6. Okay, so that's pretty much it. So that is the U statistic. And when we later on go into Python on our actual data, the U statistic, the value we get is 8,274.5. And of course, you don't just look at U statistic, right? I mean, what does that mean? It doesn't mean anything unless you look at the p-values. I explained in depth what p-value is in the last tutorial. I seriously urge you to look at it. Otherwise, the p looks like a mystery. It's like, what the heck? Okay, I get less than 0.05. So what? You have to understand what that p is, and I explained that in the last tutorial. And from now on, I assume you know what these p-values are. Every statistic that you perform, there is some sort of a metric, typically p-value, for example, that you look at. And if it's below a certain threshold, you say, okay, I have more confidence that my null hypothesis is disproved or it has been proven, and so on. So here in our real example, the U statistics came out to be 8,274. It doesn't matter what the U statistic is, the exact value. What matters is the p-value. Is the p-value much less, which basically is it compares your U statistic to all the distribution of these values, and then says, okay, the U statistic you got is so low in probability that there is a good chance that the null hypothesis is disproven, right? That's basically what the p-value is. I bet for those of you who did not watch the last tutorial, you're like, okay, what does that mean? Please go back and check. Okay, so in our case, which we will see later on, our p-value is 0.000. If I print out to like 5-6 decimals, we may see some number there, which basically practically tells us null hypothesis, the distributions are the same. We are going to reject the null hypothesis that the distributions are the same. It's a double negative, which basically means the distributions are different, not the same. And on top of the p-value, I'll also talk about the effect size. In the last tutorial, we talked about Cohen's d effect size. This tells you the magnitude of the effect. In our case, we got a value of 0.23, which is about a medium effect, right? Slightly less than a medium effect. So the summary of this distribution, after doing our Mann-Whitney U test and looking at p-value and effect size, is that the distributions for when it comes to age for these two values, whether there is heart disease or no heart disease, there's statistically significant difference between these two groups. That's the conclusion here. Okay, now on our own data, again, we typically look at plots, right? So if you look at the box plot on the left-hand side, you can see that one is, the right-hand side is higher. That means with heart disease, the average age gets to be, or median age gets to be a bit older compared to no heart disease data set in this case. Same with the Violin plots if you're more comfortable with Violin, and histogram is very obvious. As you can see, the yellow plot shows you slightly skewed towards the right-hand side or moved to the right-hand side compared to the blue or purple plot. And I want to focus a bit on the bottom right part, which is empirical cumulative distribution of age, ECDA plot. This is also quite common to report these, and let's focus on this specific plot right here. What does it tell us? Well, you pick a specific spot. For example, let's say age 50. If you just draw a vertical line at age 50, in the orange plot, which represents with heart disease, that tells us that age 50 and lower, we have 20% of data is age 50 or lower. That means the other 80% are older than age 50, which means we have more old people represented in this data, in this specific orange data, which basically is with heart disease compared to the blue one. So 40% of people of age group here it's only 20%, 50 or younger. So it tells us that much younger when you look at the blue. Okay, so Mann-Whitney U test is a test that compares or tests if one distribution tends to have large values than the other. This ECDF goes along with it because it gives you a visual representation of this test by showing you how the distributions are changing or different across the entire range of these values. Okay. And of course, I explained what these two groups are, so you can go ahead and look at these later on, but no point in reading the text. Please listen if you can. So now, in the earlier exercise, we just compared independent groups, right? So these two are independent. The people or the population that's in the heart disease is different than the population that's representing no heart disease, right? You cannot have the same person categorized into both heart disease and no heart disease. So it's either this or that. So these are unpaired groups. Now, what if you want to test whether a new diet plan, okay, someone has heart disease, for example. Now you have a population of people with heart disease. Now you want to test whether your new diet plan reduces cholesterol levels in heart disease patients. So you take only the heart disease patients and you say, okay, this is our new diet plan. And then you measure the cholesterol levels before and after the diet plan. Now you're no more independent, right? So now this is paired, or I think we should say unpaired or paired. We call it paired because it's exactly the same individual, but before and after, right? So after the diet plan. So in this case, the previous tests will not work. You need a non-independent or a paired test. And basically, Mann-Whitney is for, the paired test here is called Wilcoxon sign rank test that we'll look at in a second. But Mann-Whitney is for non-parametric unpaired data, right? We just looked at Mann-Whitney. Think of Wilcoxon sign rank test is for non-parametric paired data. There are too many terms here. Non-parametric is what we are looking at in this tutorial altogether, which means we don't have normality. The variances are not similar. So that's non-parametric. Within non-parametric, we just looked at unpaired until now, right? Where you looked at Mann-Whitney. Now we're going to look at paired test, which is the same patient before and after. Think of it like that. And for that, we are going to use something called Wilcoxon signed rank test for this paired. And it's basically, we covered something similar in the last tutorial when we did parametric tests. We had a paired sample t-test. Think of Wilcoxon signed rank t-test or signed rank test as similar to that one or equivalent to that one, let's say. Yeah, it tests differences between the paired measurements. That's pretty much it. Now, in this case, it actually considers both the sign and magnitude of differences. For example, if the cholesterol went down by 10 points, it does matter. It went down, right? So the negative sign matters and 10 points matters. There is also something called sign test, just a sign test. It doesn't care about is it 10 points, is it 2 points, is it 1 point, is it 1,000 points? Well, it cannot be 1,000 for cholesterol, but you get the point. It doesn't matter by how much, but it does matter if it went down or up. So the sign test is a very simplistic form of Wilcoxon sign rank test where it only looks at the sign. I'm not going to talk about that, but I'm going to show you that as part of coding, but I am definitely going to talk about the sign rank test. Here is a worked out example. I learned by looking at worked out examples rather than a bunch of equations, and I hope you too, you also learn exactly the same way. So I'm putting these, adding these worked out examples, and then we'll get to code. That's the easy part. Let SciPy or whatever the package do the job for you. So we measured cholesterol levels before and after the diet in 6 patients. Well, this is some data I made up. So there is patient A, B, C, D, E, F. And before you have certain measurements for cholesterol and after you have certain measurements. In all the cases, it's all negative, except one patient, it didn't change. Now the question is the median change significantly different from 0? Which means is your diet plan working or not working? Right? Let's work this out using Wilcoxon signed rank t-test. Step number 1, remove 0 differences. So our patient number C showed 0 difference. So we don't care, just remove that person. If it's positive or negative, keep it. So here is the table again after removing patient C. So we have A, B, D, E, F, and then the difference is -20, -5, and then we look at absolute difference, again, absolute values, and then the sign is negative. The rank, you typically rank them as 1, 2, 3, 4, 5, right? In this case, we have 5 patients, but 3 of those patients have exactly the same absolute difference of a value of 5. So instead of ranking them 1, 2, 3, we take the average of 1, 2, 3, which is 2, and then assign the same rank to all of those. That's how it's done. Yeah, in case you wonder why we have 3 2s over there. Next step is summing all the ranks. Okay, sum of negative ranks. In our case, we only have negatives. So let's go ahead and sum all of those. So rank 5 plus 2 plus 4 plus 2, and we get 15. And sum of positive ranks is 0 because we have nothing that's positive. Okay, since all are negative. So Wilcoxon test statistics, it is the smaller of both. So in this case, we are going to take 0 as the test statistic. That's it. That's as simple as it. Now, this is the calculation I'm showing you here is for small data sets, which it is on the screen right now. For very large data sets, you can use Z approximation, and the formula is given on the screen right there. Okay. And in fact, when you use SciPy or any of these Python libraries, it actually looks at length of the data. I believe if it's like greater than 15 or something, then it automatically switches to the Z approximation. Otherwise, it uses the same calculation that I'm showing you on the screen right here. Okay. Now, you have this, and now let's look at the effect size. I mean, previously in the last tutorial, we looked at the Cohen's D, And but again, very similar to how a p-value tells you whether there is a difference or not, right? So if the p-value is less than 0.05, we say, okay, I'm going to reject the null hypothesis. So similarly, an effect size tells you how much of a difference there is, because p doesn't tell you how much. P-value of 0.001 and 0.000001 doesn't mean anything. All it tells you is, hey, it's less than 0.05, so I am going to reject the null hypothesis. But by how much, then you need to calculate the effect size. And again, for Mann-Whitney U test, the effect size is given by the R, effect size equals to z over square root of n, and z is the test metric, whatever the test, the Mann-Whitney U test result, and n is n1 plus n2, the total sample size right there. Similarly for Wilcoxon sign rank test, it's very similar, z over square root of n. Okay, and typically when the R value is about around 0.1, we say, okay, there is a small effect, 0.3 is medium effect, and 0.5 or above, it's a very large effect. Rule of thumb. Okay, and the packages that typically offer all the required libraries, I mean, there are many packages. SciPy.stats is something where I would look at first before moving on to anything else. And you'll have Mann-Whitney, Wilcoxon, and all the t-test and everything in there. Finally, before jumping into code, a decision framework. This is something I took a little while, as you can tell, in putting together a flowchart in terms of what to use. You start, and then are the samples paired or unpaired? If the samples are not paired, independent, right? Then the next question is, are both samples normally distributed? It has to be both. It cannot be just one. Is with heart disease and without heart disease, right? Are they both normally distributed if you're looking for age metric? Okay. If the answer is yes, then you look at, are the variances equal, which means are they kind of similarly distributed? Then it's a straightforward t-test, right? It's a, but if the variance is not equal, then it's Welch's t-test. Similarly, if both samples are not normally distributed, which means they're non-parametric, we just learned about it, then it is Mann-Whitney U test. If it's not applicable, when would it not be applicable? Obviously, if it's categorical data, right? Then you look at, do you have expected counts less than, greater than or equal to 5 in all the cells, and then you actually get chi-square test. If you don't know what I'm talking about, what do you mean by cells? Again, check out the last video where we talked about chi-square test and where we actually looked at contingency table, where you plot, these rows and columns, and you add along the rows, add along the columns, and then plug them into an equation to calculate your chi-squared. But again, this is just a rule of thumb, greater than or equal to 5 in all cells, then okay, go ahead and use the chi-squared. If not, go ahead and use Fisher's exact test. So this is a decent, I hope, flowchart that you will find useful. And the ones in pink, like Shapiro-Wilk test, which we will be using, these are the tests that help you quantify whether something is normally distributed or not, for example. And Levene's test, for example, can tell you if the variance is equal or similar between both data sets. And the KS symmetry test, in a way, this is not really a symmetry test. What KS symmetry test does is it actually splits the data at the median and looks at the below and the above, and it kind of tells you whether it is symmetric, infers whether the data is symmetrically distributed or not. We'll do that again, I believe, in this tutorial. So this one, feel free to take a screenshot of this one. I find this to be very, very useful. I created a crude version of this a long time ago, and now I kind of redid this in PowerPoint. Okay, I think we are ready to jump into the code. So let's go ahead and open our Google Colab. Okay, so here is the Colab, and again, I'm going to share the file so you can directly open it in your Colab or local notebook and reproduce or repeat whatever you see here. Again, the step one, I'm zooming in so much so you can kind of see this even on your phones if you're actually checking these videos on your phone. And also, it gives me a chance not to wear my glasses when I'm actually looking at the screen. Makes me look probably slightly less ugly in in the camera right there. Okay, we start with our typical libraries like pandas to actually capture the data into a data frame, NumPy, of course, to handle our arrays. For plotting, we are using matplotlib and seaborn, and scipy.stats. Of course, that's the bread and butter for this specific tutorial, right? Or the and stat models. We are getting some utility tools from here. We'll see those later. I am going to suppress certain warnings because you may get some warnings, so that's why I imported that. And of course, the key scipy.stats, I'm going to get chi-square contingency, so you can actually, I'm not even sure if I'm using the contingency table in this tutorial, and Mann-Whitney, Wilcoxon, rank sums, and Fisher exact median test, binomial test, when we do the sign test. So all of these, and let's go ahead and run that cell. So we can, in Google Colab, SciPy comes pre-installed, pandas and others, obviously on your local environments. No need to mention, you have to install those libraries. Okay, when it comes to data, you can actually download the CSV file directly, or you can use this link. Here it gives you the data set, but the data here does not have column names, so I just added the column names right here. You get this from the documentation, and I keep forgetting what these THALACH and THAL mean, and some of these actually mean I have to go back and look at the documentation, or I usually add some notes right around here. But either way, these are all the column names, and let's go ahead and read the CSV file, and then let's look at the top 5 rows, and also let's go ahead and look at the information and then check if there are any null rows or null values. If so, we can actually fill those null values with median values right there. Okay, so just data loading and data cleanup right there, and you can see the first 5 rows. You have the age, you have sex, and you have CP is, I think, whether it has, where is it? Yeah, I think that's, oh no, target. Target is whether someone has heart disease or not. Like target is 0, 1, 2. Well, I think I should explain this. You may think that, okay, why do I have 0, 2, for example? Shouldn't it have only 0 and 1 because it's without heart disease and with heart disease? This data set apparently shows different levels of heart disease like 1, 2, 3, 4. And in the code, we are going to actually say binarize them, basically saying if it's 0, 0, if not, if it's any other value, go ahead and change that to 1, meaning no heart disease and yes heart disease, right? So that's what we are going to do later on, but that's a quick note right there. Okay, and you have cholesterol values right there, and you have, I think this is like the heart rate while exercising or something. We'll look at that later on. Okay, and here is a quick summary. Now, convert target variables to binary. I just mentioned about this because we just want binary, 0 or 1. So we are going to look at the target values. If it's 0, fine. If not, go ahead and change all the other values to 1. Similarly, the sex or the gender, we have 0s and 1s. I'm going to change them into female and male, so we know when we plot and when we look at the data, it's more readable that way. So let's go ahead and do that, and also describe the data set, which means it just gives you descriptive statistics. We covered this in the last couple of tutorials. So it tells you, okay, the age, we have total 303 data points with mean of 54.4 and standard deviation, and 50th percentile is around 56, and below and above and so on. Okay. Yeah, so that's pretty much it for, and you can go through the notes. Most of the notes here is something I copied and pasted from my PowerPoint presentation, so you should hopefully find this to be very useful. But more importantly, let's jump into our actual problem, which is, is age, for example, a factor when it comes to heart disease, or is cholesterol a factor when it comes to heart disease, and so on. So to do that, let's first of all, these are non-parametric tests we are planning on performing. But before picking whether you want to do parametric or non-parametric, step 1, check for normality. That should be step 1 all the time. And that's exactly what we are doing here with this function, checking the normality. And how do you check for normality? Of course, you look at histogram plot. By looking at it, you can tell, you can do QQ plot. If it lines up along the diagonal, you know that, okay, that's kind of close to normal. But if you want a quantitative value, then Shapiro-Wilk test will actually give you values that you can look at, and you set up certain threshold. In our case, we set what did I set alpha to? 0.05. So I say if the Shapiro value is less than 0.05, then the data significantly deviates from a normal distribution. If not, it does not deviate from normal distribution. So go ahead and use a parametric test, assuming both groups, have the normal distribution. Even if one group differs, then non-parametric is ideal. I think that's it. And we are kind of testing this normality for age and cholesterol. These are the two we are looking at. So let's go ahead and run. And we should see a whole bunch of plots and some text that's reported. So there you go. And let me scroll up so you can see it a bit clearly. Okay, so checking for normality age. By looking at this, it's not bad. Also, this one, it's still, of course, not lined up along the diagonal. But this is where I think parametric test is probably also okay. But of course, this is not really a normal by looking at it. And if you look at Shapiro-Wilk test, the statistic is 0.9677. Again, that means nothing until you look at p-value. P-value is 0.002, and it's less than technically 0.05. So non-parametric test be more appropriate, right? Because it deviates from normalcy. This looks more normal to me. There's no disease group. This is with disease, and this is no disease. And you see how it lined up nicely along the diagonal, and I bet it says a parametric test. Yeah. So the p-value is 0.13, which is greater than 0.05, which basically based on our threshold that we just set, it's significant evidence against normality. No significant evidence against normality, so parametric test is okay. In this case, I think the age, when you do non-parametric and parametric, it's okay because both are almost close to normal. And this one is also, if you look at the cholesterol, this is the disease group. Let's see what it says. The parametric test is likely appropriate because no significant evidence against normality. Here, it's definitely skewed to one side. As you can see, you have outliers on one side right there. So it probably tells us it's significantly, you see p-value is 0.0000. That tells us it deviates from normal distribution. So non-parametric test would be ideal in this case. Okay. Let's directly jump to the Mann-Whitney U test. Again, this is the easy part. Once you understand what it's doing, now you just need to go to SciPy and get the right, method from SciPy library. Okay, performing Mann-Whitney test. Again, I have a lot of code here to test a few different things, but it's just a single line of code, right, to perform this Mann-Whitney U test. All I'm printing out here is ensure that data only has two groups, first of all, because it only works on two groups, right? So do we have no heart disease and with heart disease? That's why I'm actually plotting out, printing out unique. Do we have only two unique? Then basically continue. Otherwise, hey, you must have only two. And then we divide the data into group 1 and group 2 because we have two unique ones. And then we are looking at N1, N2, total number, how much, what's the population of each, means and standard deviation, interquartile range. I'm just printing all of those. So it's a bit more descriptive, right? Descriptive statistics. And performing the Mann-Whitney U test itself is just calling this, giving it group 1, group 2, and that's pretty much it. And alternative equal to two-sided because we have two-tailed test right here. We have two that we're comparing right there. So when you perform Mann-Whitney U, it actually gives you U statistic and p-value, and that's enough for you. And for effect size, again, I'm calculating the z-score right here for effect size. Remember, you can, anyway, I don't want to deviate. Z-score is given by this formula, which is U statistic. We have U statistic, and mean of U, we have that, and standard deviation, that's what we're calculating. And then we can calculate effect size. And then I'm just printing out saying that if the effect size, remember the 0.1, 0.3, and 0.5 limits that we kind of set, basically saying that, hey, go ahead and print that out on screen. I think that's pretty much it. And then a bunch of plots. Yeah, of course. Yeah, I did talk about ECDF, right? Interquartile range, the empirical cumulative distribution function, and I should have just looked right there. So empirical cumulative distribution function plot, where you can actually look at a specific age and say, okay, what percentage of people are in that group fall below that specific age, and that's the plot right there. All I'm doing is just very simple sorting and then just plotting what percentage, and that's pretty much it. I think that's all in this block of code, and let's go ahead and then also adding p-value on the plot. That's pretty much it. And we are doing that. We are calling that function for a few different things, like for example, age, cholesterol, and heart rate, and blood pressure values. So, and let's go ahead and check how it looks for these. And let's go all the way to the top. Descriptive statistics, I always like to have this in front of me. That's why I try to print those when I look at other data. So just in case you wonder, our U statistic 8274, I showed this in our PowerPoint slide, and effect size is here, and the distribution are significantly different is what it says. And we looked at this in the PowerPoint slide, so no point in spending a lot of time looking at that. Cholesterol is a bit tricky, right? So is that really different, significantly different? We don't know. That's why we perform these tests. And result is statistically significant difference between the groups based on the test that we just performed, because the p-value is actually p-value is 0.035. Technically it's less than 0.05, so we can say it's different, but it's again effect size is a small effect, as you can see right there. So it's kind of different. Again, it tells you what you see here. It quantifies what you see. You see that, hey, I can see that these are different, but they're not significantly different. That's exactly what you find out here. And you can go through others. This is obviously, just by looking at this, I can tell that's significantly different, right? So in this case, you don't see that. These two are significantly different when it comes to cholesterol. But when it comes to heart rate, of course, you see how different these are. And this is ECDF is great, actually, to visually infer the difference between these two groups. Okay, there you go. That's Mann-Whitney U test, and let's go ahead and do Wilcoxon signed rank test. Of course, our data set is not before and after. It's not like paired data, so we have to simulate some data for paired data. That's exactly what we are trying to do here. So we're trying to do some before and after, simulate some before and after data, and then once you simulate, then let's go ahead and perform these z statistic and the mean difference. And by the way, I should have showed you where the Wilcoxon, where is it? Right there. So I mean, we did. Oh, actually, I should go through at least a couple of these. So to perform this, make sure the data is of equal length is something we look at, because before and after should be exactly the same. You cannot have different values for before and after. You need to have the same people, before and after. So first check that. The next thing is you calculate the differences after data minus before. You have to look at the differences, and this difference is what you need to check whether there is normality or not, right? So check whether the differences are symmetric around the mean. So that's another one that we need to check. And for that, we are actually, just looking at the median and then looking at the distances from the median between these above and below. One way of testing that. And KS test or Kolmogorov and Smirnov test. It can also be used to check if the distributions are similar. Again, you look at above the median and below the median. And again, you can set a threshold of 0.05 and say, hey, if it's less than 0.05, you reject the null hypothesis. If all of that makes sense, then you perform the Wilcoxon signed rank test, which is again pretty much very similar. Wilcoxon right there, before data, after data, that's pretty much it. Running these tests is easy. Whether to run this test or not, the knowledge you need to have, that's exactly what I'm hoping you will gain from these tutorials here. Running them is straightforward. Someone else did the hard job of actually coding it. We are just calling that library. Okay, and we'll go ahead and print that out. Let's go ahead and run this so you can actually see the output. Again, these are before and after simulated data. Try to find some real data where, I mean, this part is the simulation part. I'm just, as you can see, random. Around the random, we had some noise just to get before and after this. And I believe in scenario 1, there is a moderate treatment effect. We add moderate noise, and the next one is small treatment effect. We add small noise right there. That's basically what we simulated. And you should see, if I scroll down, you should see scenario 1, moderate treatment effect. And here you can see before and after. The blood pressure went down after. Good. Whatever you're doing is working. The diet is working. So, and these type of plots can be very useful. That shows you the average before, average after, and each line is before and after for each data point, right? Each patient in this case. And yeah, some of these plots, go ahead and look at it at your time, and small treatment effect right there. And again, look at the statistic. I think at this point, I don't want to waste your time just showing you every little detail. I've also included the sign test. Let me zoom out a bit because there's way too much squeezed into one screen. Sign test is, again, I added some notes. I did not explain it. Basically, it doesn't consider magnitude. It only considers the sign. It's very similar to the previous one right there, except here it only looks at the sign. That's it. Nothing more to explain. And again, nothing more to explain when it comes to how to use it, because as part of SciPy, we're going to import .stats. We're going to import the right thing, and everything else is the same. Literally, not much to explain right there. I just added a few different type of plots, if I remember, just so you can see what type of plots can you. This is sometimes, this is where I look at some literature to get ideas on new ways to display data. I love plots. I love new ways to display. And that's why I included whatever knowledge I have, all the types of plots, so you can copy the code and use it, whatever makes sense for your specific scenario. Okay, now what's remaining? Comparing the parametric and non-parametric, and then we'll stop this video. I bet this is going to be about 45 minutes at least. So I'm just I'm doing the t-test and also the Mann-Whitney U test here. T-test, we covered that in the last tutorial, and the U-test, obviously, we just did that. And then and I'm just printing out the results. Why? Well, typically you look at both, and then you see if something is severely contradicting each other, and then investigate why something is severely contradicting. So all I'm doing is just performing both and then printing out here. And if you look at, for example, parametric, normality check, of course, non-normal, this is normal, right? When it comes to age. When it comes to age, we already know. So, but it's not really extremely non-normal. It's very similar to normal. So both parametric and non-parametric should be appropriate in this case, even though we only have 300 data points, or 150-ish per group. We have unequal variances slightly again, and parametric t-test is telling us the difference is significant. And also the non-parametric is telling us the difference is significant, right? So they match, great. And most of the time they should match. Here it says not significant and significant. It's in both cases, it's very similar. I would say the effect size here is 0.17. Here it's 0.12. This is more close to 0.2 than this one. So it says not significant, and this is significant. But again, this is basically coincidence. Of course, this is the effect size R. Okay, so yeah, I think not much to say there. And comparing paired tests is another one. So that was the unpaired, and this is the paired test using the same simulated data that we just had earlier. So you can go ahead and see there's a lot of you don't need this much code. I added all this code. In fact, I took help of ChatGPT to actually add a lot of annotations to my code, a lot of print statements to my code, because once I have a nice structure, I just want to add a lot of information, because this is a tutorial video, right? And also get some nice colors going on, and that's what you see right there. But the actual meat of the code is just a few lines of code. You can strip it down if you want. Okay, there you go. There is the comparison between both and distribution of the differences. And again, this is the differences, right, before and after when it is paired. And the distribution is, it looks normal here, but obviously it's going wonky right there. It's not even close to the diagonal. So it's definitely not normal distributed. Okay, so I hope you learned something here, and in the next tutorial, let's actually, I believe we are going to look at comparing multiple groups, not just two groups. That's the plan. I hope I'll stick to the plan, and I will see you in the next tutorial. And again, please subscribe to this channel if you haven't already done so. Thank you very much.